All right, cool. All right. Grokking Big O, algorithms and data structures. So the goal by the time this presentation is done is just to give you hopefully the simplest explanation of Big O that you've ever heard. That's my goal. If you want to find more information and resources that I put together around interview prep, around what it's like to work for a FANG company, especially as someone who's Black and comes from an underrepresented background, I've got tons of articles and resources there. I tell you exactly how I studied. I share information around how to not just navigate the interview, but how to think about your career, how to be a good problem solver as an engineer, all of that stuff. So you'll find that on my page. And if you want to book me to speak, I do that too. I mean, holla at your boy. I am happy to give whatever kind of talk you need. All right, cool. So again, that's all at anthonydmays.com. Like I said, you can follow me on all the different platforms. All right, cool. Let's jump into it. So if you ever get confused and you can't remember my name or any of that stuff, all you have to do is just type in Compton in Google and I will be your first search result. I'm telling you right now, that's how you find me. As I mentioned before, I've been told that I have quite an inspirational story and I love to share it. And so if you ever need to find me, just type in Compton in Google. I'll be right there. So what qualifies me to give you this talk on algorithms, data structures, and Big O? What qualifies me? Well, I love that, about a month ago or so, a little over a month ago, I put a tweet thread, which I think is still pinned on my profile on Twitter, where I just talked about the things that I did to specifically practice interview questions in preparation for the Google interview that I passed back in 2013. And so I talked about how to leak code correctly. And someone, my homie Chloe, was like, yeah, so what makes you the one to talk about this stuff? And so I replied to that tweet and just basically said, yeah, I was supposed to get my CS degree on the 3-year plan. I got it on 5. I took my algorithms course 3 times because I sucked and didn't take it seriously and struggled and slept through the final my second time around. So I took it 3 times. And I failed my Google interview on my first attempt. So I've done everything the wrong way before learning how to actually do it correctly. So that's my experience. That's what brings me before you today. This wasn't me being super smart or super skilled or anything like that. It literally was me failing and doing it the wrong ways, and then coming around to add discipline and the right information to succeed. So again, I don't want you thinking that you've got to be a genius to understand this stuff. You really don't. You need the right information, which I'm going to give you now, and then you need the work ethic after that. All right, there's 3 things that I want to talk about in this short presentation. One is why we care about Big O. It's important to talk about motivation because I don't think you're going to care about what Big O is until you understand why you should know it. So we're going to talk about why you should care about Big O. Secondly, we're going to talk about what Big O is. So give a definition and kind of walk through that. And then lastly, I'm going to talk about how to use Big O as a tool to optimize your code and make it better. So that's what we're going to do. We're going to talk about why you should care about Big O. We're going to talk about what it is, and then we're going to discuss how to use that as a tool for writing code at scale. All right. And we're, of course, going to incorporate algorithms and data structures as we're talking about that. Okay. So why should you care about Big O? Big O helps you to build code that scales. Helps you to build code that scales. So I know that many of you, no secret, have ambitions to work at FANG companies. And these companies work at just obscene scale. So if you look at, for instance, Amazon, 98 million mobile users and growing, right? 98 million mobile users. At Google, 40,000 searches per second at least. And that's an old stat, okay? 40,000 searches per second on Google.
Sorry, I don't know how to do that.
I forgot to turn
Here
off the
are other
stupid
things you
assistant.
can try.
Every single time I want to go live, I can't
Microsoft.
take you nowhere. So thank you, honey. I appreciate that. And then Netflix has 200 million users, right? We're not going to talk about the stuff that's been happening lately, but whatever, right? So these are really large numbers. And if you are thinking about joining these companies and working at any point along the pipeline that's touching these huge numbers, you need to understand how to write code that's going to survive inputs in the millions or billions, et cetera, right? So that's really what Big O helps you do. It helps you to write code that can scale to large numbers, large distances, et cetera. So that's the technical reason why you should care about Big O. But there's a second reason why you should care about Big O. You want to know what it is? Get paid. You want to get that money, right? You want to get that bag. You want to call your parents with bundles of cash in your hands, right? Because you were able to get that job at Google or at Amazon or Meta. I'm not going to take anything away from doing meaningful work and all that stuff and have an impact on the world. Like, I totally get that. But at the end of the day, a brother needs to make money, because I grew up poor, right? And it turns out that those really lucrative job offers, those lucrative opportunities, comes to engineers who know this stuff and know how to use algorithms and data structures effectively. All right. So if that gives you a chuckle, that's totally cool. But for those of you who know, you know, right? Like, we all trying to get that bag. And for some of us, what might be the impediment is knowing these concepts that help you to succeed at those high level interviews. Now, I will say this: even if you can have a perfectly happy, fulfilled life in tech, doing engineering, writing code, et cetera, without knowing Big O, algorithms, and data structures. You can totally do that. You can make good money doing this, have a fulfilling career. I had a fulfilling career for 13 years before I got to Google. I enjoyed what I was doing. I didn't really have to bother with Big O, algorithms, and data structures that much. Let me just keep it 100. But when I did practice and learn that and start to use it and ended up getting an offer at Google, that became just another transformative step in my career. So I just want to break that down for you, right? Like, you need to understand that. Okay, let's keep going. All right, so what is Big O? So we've talked about the motivations, about why we use Big O for optimizing code, and then, like I said, honestly, getting that bag. Now let's talk about what it actually is, because hopefully I've piqued your interest enough that you now care. This is what Big O is designed to do. It describes the performance of code relative to its input in the worst case. Let me say that again. Big O is used to describe the performance of code, and we're going to talk about what we mean by performance, relative to its input, right? So code takes some input and then produces an output. Like, we're just going to simplify that way. And it measures that performance in the worst case. Okay, that last part is very important. Okay, so there's two senses in which we talk about performance. One is something called time complexity. And I have time in quotes because there really isn't much about time relating to this. I mean, obviously code is going to take some time to run. So from that, we care about using this as a proxy for that. But really it's about how much work your algorithm has to do given the size of its input. So how much work do I have to do? And we're going to come back to this idea of work or operations that your code needs to accomplish in order to be successful. So how much work will I have to do? And then there's space complexity. How much space do I have to use in order to accomplish the task that I need to accomplish? So time complexity, space complexity, these are two things you're going to hear about when we're talking about Big O. Another fancy phrase for this is algorithmic times complexity or algorithmic space complexity. Okay. So those are the two senses which we care about code performance principally when it comes to Big O. Okay, I'm going to use a table to kind of break down what I mean by measuring the performance relative to input. So these numbers are completely made up. They're not real. I'm just using them for illustration purposes. All right, so I just want you to follow along with me. So let's say that we've got some code, and we've got on the left-hand column input of various sizes. So maybe your function is going to process 10 elements, 100 elements, 1,000 elements, 10,000 elements, or 100,000 elements, right? So that's the size of input. At each row, we get bigger and bigger. Let's say that we have an algorithm that runs in Big O of one time, okay? Or what we would call constant time. That's the nickname. So for an algorithm that runs in constant time, we're basically just going to do the same amount of work no matter what our input is, right? So if my function just does one thing, it's just going to always do that one thing. It doesn't matter if I have 100,000 things, a million things, a billion things. I'm only ever going to do one unit of work, period. That's it. Okay. So as the size of my input changes, the amount of my work does not change. It remains constant. And that's why we call big O of 1 constant time or constant space. All right, next we've got something that is big O of log base 2 of n time. Okay, so our big O of log n time. We shorten it because in computer science, we almost always mean log base 2. So big O of log n, or logarithmic time, identifies an algorithm in which, the number of operations are basically going to be relative to log base 2 of whatever the size of the input is. So if I've got 10 elements, take log base 10 of that, or log base 2 of 10, that basically gets you 3. I'm rounding things, so it's not precise. So for 10 elements, I've got to do basically 3 units of work. For 100 elements, 7 units of work. Again, these numbers aren't real, just these are for illustrative purposes. Big O of log base 2 of 1,000 is basically 10, right? And so you can see that as the size of my input grows, I need to do more work, okay? But the amount of work that I have to do is described basically as log base 2 of whatever my input is. Okay, so that's how that works. You can almost plug the size of your input into that mathematical formula there to figure out about how much work you're going to have to do. And as you can see, it's growing, but it's not growing by that much. Okay, so that's logarithmic time. Now let's look at linear time. Okay, so big O of n. Basically, for the size of input that I have, I'm going to do a corresponding amount of work for that input. And that relationship is linear. Okay, so if I've got 10 inputs, I'm going to do about 10 units of work. If I've got 100 inputs, I'm going to do about 100 units of work, or 100 operations, however you choose to call it. 1,000, I'm going to do 1,000 units of work, right? So as my input grows, I'm going to have to do about as much work to keep up. Okay, so that's what linear time, that's basically what linear time looks like. Now let's take a look at quadratic time, something that runs in big O of n squared time, okay, or does big O of n squared operations. We call that quadratic, and it's just a hot mess. Right? So for 10 elements, I've got to do 100 units of work because 10 squared is 100. If I've got 100 items, now it's 10,000, right? And as my input changes, I've got to do way more work, right? So for 100 elements, something that runs in big O of n squared time only has to do about 10,000 operations. Something that's linear 100, something that's logarithmic 7. So you can see how based upon how I code my algorithm, based upon how I write my code, if I understand the performance of that, I can plan for what is going to happen as I get more and more input. So hopefully this is breaking things down a bit for you. You can almost also think about this in terms of golf. So the lower the score, the better you're doing. And similarly in big O, we want that math formula to be as low as possible, right? So ultimately, I can't do any better than constant time. Like that's the best. The next best is logarithmic. That's still pretty good, not too bad. Linear, it can do it. Sometimes that's necessary. I definitely don't want to be doing quadratic stuff, right? I don't want to have to be doing so much work that now, as my input grows, I'm just blowing the roof off of things, okay? So this is what big O helps us to do as we're estimating the performance of our code. Okay, cool. So we've talked about why you should care about big O. We've talked about what big O actually is. Now let's talk about how we use big O as a tool to optimize our code. Okay, so let's jump right in. The key to using big O as a tool is to understand that we're trying to make the best out of the worst case. Okay, we're trying to make the best out of the worst case. Remember, big O is about measuring the performance of code relative to its input in the worst case. Okay, so the first thing that we need to do when we're looking at our code is to identify our inputs. Okay, what are the inputs that are coming into our code? We want to understand that part. Cool. So let's take a look at this function right here. All right, so I have this function on I'm choosing to do all my examples in TypeScript because that's the last language that I work with the most. So that's what it is. So I've got this TypeScript code, and yes, we use algorithms, data structures, and big O on the front end. All right, get over yourself. Like if you're a front end engineer, you should be learning this stuff too. But I digress. So I I can't be that saucy with y'all. Let me calm down. So with this function, what would you say are the inputs here? Okay, and unfortunately, I'm not going to wait for y'all to answer because there's a log with the streaming. So I'm just going to tell you. When we look at this function, the input clearly is names, right? So I'm going to take in a list of names or a string array of names, and I'm going to do some work on those names. In this case, this function just prints the name to console, right? So that's my input in that example. Let's look at a more complicated example. So now I've got this new function that's going to take some words and it's going to get some lyrics and it's going to find where those words occur in the song lyrics and then return those indices as the result of this function. So, what are the inputs to this method? Well, you would probably say words, and you'd be absolutely correct. But there's also a second input, and that second input involves the lyrics that we're reading from somewhere. Okay, so I use this example to highlight the fact that your inputs may not always be just in the arguments of whatever function you're building or whatever code you're building. Anytime you're pulling data into your function or into your method, that's considered input for the purposes of measuring the performance of our code. All right, so just want you to understand that. All right, so once we know what our inputs are, now we need to identify what's the worst case. What's the worst case situation? I laugh because I grew up, early in my career, I would take the train, the light rail to work, and I would take the blue line. I think they changed the name of it recently, but there's a blue line train that runs through LA. And, I catch it at COMPTON station and it goes through Watts, South Central, et cetera, until it gets to downtown LA. And, if you've never been to LA, boy, you can see some characters on the blue line. Like it can be a situation. And, I've seen some things during rush hour that, folks shouldn't have to see. But I would carry this little survival handbook because, I wanted to, if a situation was popping off, I wanted to figure out, like, if I got to jump from this train, like, how should I best roll, little things like that. I mean, I bought this little book for humor, but low key, brother's just trying to be prepared. So, I was always thinking about worst case scenarios, like what happens if I'm in this situation? How do I plan and think about that? So just let's go through this exercise of worst case scenarios. So let's suppose that we are dealing with a burning building, right? And our job is to, be firefighters and get people out of the building. The best case scenario in this situation is that the whole building is empty, that there are no human beings in the building at all, or pets for that matter, right? No living things are in the building. That's our best case scenario. But when we're measuring performance, we don't care about the best case scenario. We care about the worst case scenario. And as you can intuit, the worst case scenario is that this entire building is full of people. Okay, that's the worst case scenario. So now as we're thinking about how to get people out of the building, we've got a couple of options, right? We can take somebody from a high floor and evacuate people from a high window. That's not very ideal, right? We might be able to do it, but if you're trying to evacuate a bunch of people out of a high floor, that could be a big issue, right? And if you have to jump out of that window, God forbid, your likelihood of survival isn't going to be very high. It would be much better if you chose a window on a lower floor, okay? Because if you had to jump out of it, your survivability goes up. Maybe there's ways that we can make sure that people are able to get out a little bit faster, but it would be easier to evacuate people from the lower floor. And so I want you to kind of use this mental model as you're thinking about big O and thinking about why those lower values are better, right? But again, we're going to think about that from the perspective of the worst case scenario. All right, so let's talk about what worst case scenarios look like. Let's suppose that we're searching for something. What's our worst case scenario, right? The worst case scenario when we're searching for something is that it doesn't exist in the collection of things we're searching for, right? That's the worst case scenario. So I want my code to run well in a situation where in the worst case, nothing is in the collection, or the thing that I'm looking for isn't in the collection. And why is that the worst case? It's the worst case because I have to look through everything before I realize that the thing that I'm looking for isn't there. Okay. So some of y'all have lost stuff in the house. You don't remember where you put that thing. It turns out it wasn't even in your house, it's in the car, but you done tore up everything from the closet to the bedroom to the kitchen looking for this thing. And right, So some of y'all have been in that very horrible situation, and you understand what that worst case scenario looks like, right? All right, what if we're sorting things, right? Because sometimes we're sorting. What's the worst case scenario when we're sorting things? Well, it turns out that the worst case scenario is that the thing that we're trying to sort is already sorted. And usually the worst case is when it's sorted in the opposite direction. Why is that the worst case? Because we have to move every single thing somewhere else. Okay. That's what makes that the worst case. And so when you understand that, you need to, if you're writing code to sort something, if you're writing code to search, when you understand those use cases, then you can understand why you want to make sure your code is working as optimally as possible in those situations. Okay. So let's take this method here, right? Say hello. In the worst case scenario, what's going to happen? In the worst case scenario is I've got a lot of names and I've got to print every single one of those names. That's the worst case scenario here. And you know what? In this case, it's necessary. Like the whole point of this function is to print every single name, so we can't avoid that. So if we have n names, this is going to run in big O of n time. Okay, that's the worst case scenario. Now in this situation, going back to the find words and lyrics situation, I've got two inputs, right? I've got words and then I've got lyrics. The worst case scenario in this situation is I have a lot of words and I have a lot of lyrics, but I can't find any of the words and any of the lyrics. That's my worst case scenario in that situation, right? Because remember, this is a searching algorithm. It's going to search for words in the lyrics. And if I don't find words in the lyrics, then I'm going to do all that work for nothing, okay? Because I'm not going to find those results. So that's what I mean by worst case. And when you are gaining a mastery of Big O, you'll start to figure out how to look at an algorithm, how to look at some code and figure out, okay, what's the worst case scenario in this situation? Okay. And I highlighted the find index method because that's where that search is happening, okay, as we're looking at the words and cross-checking with the lyrics. Okay, cool. So now that we understand what our inputs are and what the worst case scenario is, now we just want to figure out where are we at right now? What's our current Big O performance? And we can talk about, again, time complexity, space complexity, but we're going to focus here on how much time does our algorithm need to spend in the worst case. Okay, so we're going to look at some code samples and we're going to talk through what the Big O of these code samples should be. Okay, here's a tip. If you want to figure out Big O quickly, the key is to look for the loops over your input. Okay, so you know what your inputs are. Anything that's looping over your input is probably going to have performance implications that can be represented in Big O. Okay, so remember, it's loops over the input. So let's say that we have this function, again, say hello. It's a little bit different than the one that I had before. All it's going to do is just console log basically names that and I realize that there's a bug in this code. Don't worry about that. Just ignore that. We're just going to do a console log statement, right? What would you say is the Big O runtime of this code? Well, do we see any loops? No, I don't see any loops. All right. Well, this is probably going to be constant time, and indeed it is, right? We're just going to, it doesn't matter whether I get one name or a million names. I'm just going to do that one thing. I'm just going to console log out whatever this string is. Okay. So that's constant time. What if I add another operation? What if I have two console log statements in here, right? Well, guess what? This is still constant time because it's still going to do the same amount of work whether I get one input or whether I get a million. Okay. Remember, we care about how the function behaves as the input grows. And in this case, it doesn't matter how many names I get. I'm just going to do the same amount of work. All right. Now, here we have modifications to the method. We've now introduced a loop. What do you think is the runtime of this algorithm? Right? You might think that, hey, we've got one loop over the input. This method runs in linear time, or Big O of n. Nope. It's not Big O of n, it's constant time. And why is it constant time? This method is still going to do the same amount of work. Why is that? Because it doesn't matter how many names I have, I'm always going to execute this loop just 100 times. If I have a million names, this loop is only going to go 100 times. Okay. Again, there's a little bit of a bug in here, but I'll fix that later. I mean, who am I kidding? I haven't fixed it yet, and it's been like 3 weeks. So whatever. But anyway, this loop is going to do the same amount of work. Doesn't matter what my input is. It's always going to do the same 100 things. So it's still constant time. Now, if you notice, I'm going to make a change to the loop so that now I'm looping over the input. I'm going to loop with respect to the number of names that I have in my array. So names.length, right? Now that I've made that change, this algorithm now runs in big O of in time, okay, or linear time. All right, so you can start to see how we're starting to understand how to look at loops over input to figure out what our big O is. All right, here's a bit of a fancy example, but I'll walk you along as best as I can. So when you're studying algorithm and data structures in big O, you're going to learn about something called a binary search tree. And this method will take a node from a binary search tree, and all it's going to do is just find the maximum value in the tree, okay? So it's a pretty simple thing. Here's what it looks like graphically. So here's a fully specified binary search tree in which each node has 2 children, or is a leaf node, in which case it won't have any children. But here's a fully specified binary tree where every parent node has exactly 2 children, okay? So, you know, our algorithm find max, all it has to do is just go along that right edge of the graph to find the maximum node, okay? That's all that we have going on here. Now, if you notice, this method is always going to do whatever the height of the tree amount of work is, okay? And it turns out that we know what the height of the tree is if we know how many nodes are in the tree, okay? So for a fully specified binary tree with 5 levels, I've got 31 nodes, and it turns out I can express the number of nodes in the tree with relation to its height. Follow me on this. You know, we'll walk along this. If you have any questions after this, let me know, but I'm trying to make sure that we're not going too fast. All right, so this tree has 31 nodes. It turns out that I can express that as 2 to the power of 5, which is the height of the tree, minus 1, okay? And this holds as I have different levels of the tree. So let's say that my tree has 4 levels. Well, 2 to the power of 4 minus 1 gives me 15 nodes. And if you quickly count all the nodes in this tree, you'll see that there are indeed 15. What if I have 3 levels? Well, 2 to the power of 3 is 1. That gives me 2 to the power of 3 minus 1 gives me 7. I have 7 nodes in this tree based upon its height. Tree of height 2, I have 3 nodes, et cetera, et cetera. Well, why is this important? Why is it important that, you know, given the number of nodes I have in the tree, that I can figure out how tall it is? Well, because I can express that as a mathematical formula that looks like this, the floor of log base 2 of n plus 1, okay? But you know what? We're in big O land. We don't care about floor. We don't care about that 1. We can get rid of all that and simplify. It's just log n, okay? Big O of log n. What does that mean? That means that if I know what my input is, and I know that my code is basically just going to be doing the amount of work for the height of the tree, I know that my algorithm is going to be big O of log n, okay? So this is why code that basically does divide and conquer, where, hey, I'm going to divide in half and I'm going to go right or left or something of that nature, that's big O of log n, okay, or logarithmic time. Now, let's say I modify this code example. I'm going to modify my say hello example. And what I'm going to do is I'm going to skip through the names in my array in powers of 2. Okay, so I'm going to look at 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, et cetera, et cetera. So I'm going to hop through that in powers of 2. Well, it turns out that it's just going to basically do exactly what we see here, right? Where it's going to go the height of the tree. And that's, as we already decided, if we know how many nodes are in our tree, it's just log n. So depending upon how many names I have coming in, I know that my function is going to run in a roughly log n amount of time. All right. So that's, or do roughly log n number of operations. Okay. So that's what that is. That is a nice trick and a hack that you might not understand right now, but there are interview questions where knowing that bit of information can do you good. All right, let's keep going. Again, taking our say hello example up a notch. Let's say that I've got 2 loops. One is nested inside of the other. Okay, now both of these loops are going over our names. Or it turns out that the big O runtime of this function is big O of n squared. Why? because for every iteration of the first loop, I'm going to loop through all the names again. That's n times n, okay, which is n squared. So again, as we look at the loops over the input, we can understand what the performance of our code is going to be. Okay, so this is going to give me some really nasty behavior if I have a lot of names coming in. What if I take the inner loop and put that on the outside? Okay, so that now they run side by side. Okay, so what do you think the big O of that would be, right? Put some guesses in the chat. What do you think is going to be the runtime performance of this code? Okay, all right, I'll give you just a second. All right, cool. So you might say, well, I've got one loop that's going n times and I've got another loop that's going n times, right? Where n is defined as the length of the names, right? So you might say big O of n plus n. Now, some of you have a little more math and you're just like, big O of n plus n, that's 2n. Because I know my algebra, Anthony. I'll be like, all right, cool, well done. But you're still wrong. In big O, we don't care about the constant. We don't care about that too. So we're just going to take that off. It's just big O of n. It's still just linear time. Okay. So I like how with big O, what we care about is just as we say, it's the shape of the curve. That's what we care about. Okay. So big O of n, linear time, boom, we're good. Okay. So even though you see two loops here, you just have to understand how those loops relate to each other to understand how the big O is working. Okay. All right. So now we've got another example where now we have 3 nested loops and each of the loops are going over the input. Okay. So for every name, we're going to have another loop over all the names. And then for every iteration of that loop, we're going to have another loop. Well, that's big O of n cubed, right? You're starting to probably figure out that the more nested loops you have over your input, it's just into that number of loops you got. Okay. So that's big O of n cubed. Not too bad, right? And as you look at this stuff more, you'll start to be able to look at your code and figure out what your big O is. All right. Now here's a tricky example. I'm just going to admit that right up front. We have a function that just does one thing, right? It just calls sort on the array of names. What do you think the runtime of this is? Right? Now, I know some of you might be thinking, this is constant time. I don't see any loops. This is constant time. And what I'll tell you is, no, it's not constant time. This method actually runs if it runs in Chrome, and obviously I'm a big Chrome fan because, stock. But anyway, with this example, I happen to know that this is big O of n log n. And why is it big O of n log n? It's because that sort is doing some work and it's not free. Okay, so this sort is still operating on my input and that has a real cost. I looked in the documentation for the VA engine in Chrome. The array sort is implemented as big O of n log n. So my method, as a consequence, is going to take big O of n log n time. That matters. Okay. This is why you should understand what your code is doing underneath the covers, because that can have a serious impact on your code and on your algorithm. All right. Cool. All right. Let's talk about how to find the best of the worst case. So now we're going to put everything together and optimize. Okay, let's go to my find words and lyrics example. All right, so as we talked about before, we've got words and we've got lyrics, and now we want to understand what's the big O runtime of this. Okay, well, for every single word that I have, I've got to find that word in some lyrics. Okay, so remember there's 2 inputs. So I'm going to say that the performance of this is big O of W times L, where W represents the number of words that I have and L represents the number of lyrics that I'm dealing with. Okay, so big O of W times L. Big O of W times L is okay, but I think that we can do better. All right, remember the big issue here is that every single time I've got to look through all the words when so I've got to look through all the lyrics for every single word. What if I didn't have to do that? Is there a way that maybe I can take that find out of the picture? Because that's going to be, I'm going to have to go through all of those words. Okay. Well, it turns out that I can introduce a data structure. All right. And this is the key of data structures, or the value of data structures, I should say. That was a poor choice of words. No pun intended. But I'm going to declare a map, and what it's going to do is I'm going to take all my lyrics and I'm going to just figure out what their index is by word. So I'm going to build that map, or a hash map or dictionary. You may discover it by different words. And because I've got to do this for all my lyrics, that's going to take big O of L time. All right, cool. And then I'm going to, for each of those words, I'm just going to use my dictionary to figure out where that word is. And it turns out that looking up things in a dictionary or in a hash map is on average constant time. Okay, big O of 1. So it's on average constant time. It's not big O of N, believe it or not. You can check me on this at bigocheatsheet.com. But on average it's 1. So I'm going to pretend like it's big O of 1 because most times that's what it is. Okay. So now it's just big O of L plus big O of W. So just big O of W plus L. W plus L is better than W times L, right? If I plugged in a number for W and plugged in a number for L, W plus L is going to be less than W times L. Okay. So there's that. So I've done better. But what if I know that the lyrics never change? What if I know that the lyrics never change? Oh, that's a very important insight. That means that I don't have to build that map in this method every single time I call it. If I can move that map building out of this function, all of a sudden my function now becomes just big O of W. Okay, so I've taken something that was big O of W times L and I've simplified it to something that runs in big O of W time, right? I'm substituting W for N. I could use whatever letters I want. I'm going to use W for clarity here. This runs linear time. Okay, so I've taken something that was big O of W times L and I've now made it linear time. And that's how I think about using big O to optimize my code to ensure better performance and behavior. All right, that's the presentation. I slowed it down a bit for the benefit of this audience because I have a little bit more time. But hopefully this was all useful. And again, you can follow me on Anthony D. Mays on all the platforms where you can find articles and tips and live streams like this, where I'm just going to be sharing useful information.